Equilibrium. In stoichiometry, you learn that in order to make a product, what limits how much product is made is limited by just the limiting reagent, okay? So if there's no more limiting reagent, no more product, okay? But we should also never assume that reactants will become products and it will always go to completion. For example, this tug of war, this person is trying to pull it to the left, this person is trying to pull it to the right. The rate of the concentration of products and reactants are, if they're going equally in opposite directions, there's actually no change in the overall concentration of these things. How is this possible? Well, reactants actually combine at the same rate as the products decomposing. For example, let's supplement it with this graph over here, N2 and H2, let's say it's this person over here. As it's combining and reacting, it's gonna decrease itself so that it can create this NH3. But why does it not go all the way down? Why is it stagnating and kind of plateauing over here? It's because, guess what? This NH3 over here, when it's being produced, it's actually going to decompose and break down back into the N2 and H2 as well. So this doesn't actually just go all the way downwards and goes down to zero concentration. It actually stagnates thanks to this NH3 going backwards. Again, it happens vice versa. Now, at equilibrium, so at this point right over here, when it's all going parallel, the substances stabilize at these different concentrations. So this one, they're obviously all different concentrations. They're obviously not equal, but at least they are still constant. Okay, so that's what equilibrium is. So this person over here, let's say in the beginning, pulls a little bit to the right at 0.5 meters a little bit, okay? At some point, it's not going to keep going. It's going to stop at 0.5 meters, let's say, and it's going to remain at equilibrium. It's not going to move, okay? So from the observer, they're going to see the rope not even moving, okay? Obviously, there's opposable forces, but to the observer, the rope has stopped moving, okay? It is still in equilibrium now. So what factors are in equilibrium systems? Well, the rate of the forward of the reaction must equal the rate of the reverse. Also, macroscopic properties, so the things that you can see with the naked eye are going to be constant like these things. It must be in a closed system, so no matter is lost to the environment, and changing conditions can also alter the effect of equilibrium by altering the equilibrium constant, which is just the ratio of products to reactants. So for example, this one over here, we moved it a little bit to the right at the beginning initially. This person had a little bit of an edge. However, it's going to stay at 0.5 meters, okay? But there can be an altering, okay, of this equilibrium if there's external perturbation like temperature, okay? This is the only factor that has an effect of this equilibrium constant that can change this whole set. An increase or decrease of this actually do not have an effect. Lastly, let's look at this question over here. This person is saying because the concentration of the reactants and products are not equal, okay, this is not at equilibrium. That's false, okay? The rate of the forward reaction must be equal to the rate of the reverse. That's it, okay? The concentrations don't have to be equal, but as long as they're constant, it can still be at equilibrium. Try this question on your own, and I'll be giving you the answers shortly. This is the answer.